Welcome back to Precalculus. For our final video of 9.3, we're going to look at the sum of geometric series or of geometric sequences or a geometric series. So let's explore this case. What if we're going to add a sequence together? So you have your first term plus your second term. I could put A2, but just to not add too many letters, I'm going to say A1 times R. That is A2, right? And not add any letters, I'm going to say A1 times R squared for the third term, A1 times R cubed for the fourth, A1 times R to the fourth for the fifth, and on and on and on, all the way up to my last term. My nth term would be A1 R to what? Did you notice that my my first term had no R's. My second term had R the first, my third R squared, my fourth R cubed, my fifth R the fourth. So this is going to be a n minus 1, where there are n terms, right? Okay, and do something kind of crazy here. I'm going to multiply both sides by r. So this will now be r s n. If I multiply by r, this is now a1r. This is now a1r squared. This is now a1r cubed. This is now a1r to the fourth. And on and on and on. And the very last one, actually, there will be an a1r to the n minus 1, and there will also be an a1r to the n. Because all the r exponents went up by 1, right? Now, we've learned in algebra, when you're solving equations simultaneously, if you have two equations, you can add them, you can subtract them, and those new equations are also valid. So what if I subtracted these two? Crazy, right? If you subtracted them, like this minus this, you get Sn minus R times S sub n. That's not very interesting. You get A1, this has no one to go with, but notice those would cancel out. Those would cancel out. Those cancel out. Those cancel out. These cancel out. That's remaining, and it's a minus. So I have this not infinite, but a finite but unknown number compressed to this known number. So remember, my goal again was to find S sub n. So if I factor out S sub n here, a little algebra move, and I'll factor out A1 here, I get that, right? And finally, I want to solve for my S sub n that's what I'm looking for. I get this peculiar expression that is the formula in the book. So this is for a sum of geometric sequence, or something that's called geometric series. Kind of cool. You don't need to know how to prove that, but I just want to show you where it comes from. Or we're going to do a handful of examples, talk a little bit about infinity, and be done. So first example is this. What is 1 plus 2 plus 4 plus 8 plus 16 plus 32? Now you could add these, right? 3, 7, 15, 31, 63. But I want to test my formula out. Let's see if we really get 63. By the way, does this look familiar? Did you know that this is the number of games in a 64-team tournament? So if you think of the NCAA basketball tournament, not including the first 4 games, but the regular 6 rounds, starting with 64 teams and 32 and so on. The first round, there are how many games? There's 32, right? Because 32 teams win, 32 lose. 64 teams, two teams in a game, so you divide by 2. The round of 32 has 16 games. The round of 16 has 8 games. The round of 8 has 4. As you get to the Final Four, the first round of the Final Four, the semifinal has 2 games. The championship has 1. So there's actually 63 games in the NCAA basketball tournament. Although a really nice way to determine that, I read this somewhere one time, that if you have a single elimination tournament it's always 1 minus the number of teams is the number of games, because you need to generate, in a 64-team tournament, you need to generate 63 losers. Every game produces a loser, 63 games. So if you have buys, regardless, if it's all as a single elimination, say you have a 81-team tournament, is going to have 80 games, because you got to generate 80 losers to crown the single champion. Okay, so using this, or using our fancy formula, I'm just going to write it again just so we can write on it. We need 3 things, just like before. You need first term, A1, got it. You need R, I have to think about that. And you need N, we can think about that too. So that's our A1. Our R, what is the common ratio? 2. Now I could have, if I had gone 32 plus 16 plus 8 plus 4 plus 2 plus 1, the common ratio would have been 1/2. But it would have been the same answer, because your A1 would have been 32, it would have evened itself out. But the common ratio is 2, check. Number of numbers, 1, 2, 3, 4, 5, 6, we can actually just count them. So if we want to find this sum of these 6 terms, our first number times 1 minus R to the n, that's just weird, over 1 minus R. You have like negatives and stuff, but they're going to all cancel. So this becomes 1 minus 32 over negative 1. Oops, I'm sorry, 1 minus 64 over negative 1, which is negative 63 over negative 1, or 63, just as we suspected. 63 games in a 64-team tournament. Let's do some with the summations. What if they had a summation and saying, I want you to find from k equals 1 to 9 this sum. Remember what I encourage you to do on these is to write out the first few terms. Negative 2 times 1 minus 1 plus negative 2 times 2 minus 1. That's probably good enough. We could write the last one, although we don't really need the last anymore. With arithmetic, we needed last. Geometric, we don't. Geometric, we need the ratio to find the sum. Arithmetic, we didn't need to know the common difference, D, to find the sum. But with geometric, we do. But I'll just go ahead and do it anyway. Negative 2, 9 minus 1. So this is, I'm going to just write these out. So this becomes 1 plus negative 2. Negative 2 to the 8th, is that 256, I think. Not that it really matters, we're not going to need it, but yeah, okay. So we have enough what we need. We know that A1 is 1, right? Got it right there. R, what is R? What times that is that? Negative 2, right? But here's a clue. In the summation problems, your R is always that base, every time. How many numbers are there? 9. You subtract the numbers and add 1. So it's 9. So we're ready to do this. So the sum of these 9 numbers is 1 times 1 minus negative 2 to the 9th over 1 minus 9. I'm sorry, it's not 9. This is why it's good to write down the equation. Let's do that. S sub n is n. Why am I using this? Is A1 times n minus 1. Okay, slow down. It is A1 times 1 minus r to the n over 1 minus r. Getting all my formulas mixed up. So 1 times 1 minus negative 2 to the 9th, 1 minus negative 2. Okay. So in other words, we get 1, that's going to be a plus 512 over 3. So 513 over 3, is this going to be a fraction? It better not, right? Look at these numbers. They're never fractions. So that's kind of a nice thing. If you get a fraction, you know something's wrong. And I get 171, which makes sense. This is going to fluctuate from positive to positive, negative, because the next biggest number is going to be negative, and it's going to dwarf all of these. So since my last number is positive, it's no surprise to see my sum is positive 171. Let's try another one out, and then we'll do our final topic. Let's mix it up and go from the 0th term this time. Okay, write the first few terms out. 2 times 4/3 to the 0 plus 2 times 4/3 to the first, all the way up to 2 times 4/3 to the 15th. Now we can do this quickly, I think. Well, let's figure out what these are. This is 2 times, that's 1, so it's 2. That's 8/3. Not that we really care. This one, I don't know what it is, but we don't care. It doesn't matter. So we know our, let's write out our formula again. A1, 1 minus r to the n over 1 minus r. So A1 is 2. What's our r? It's always that, right? Minus 4/3 to the nth power. What's n? How many numbers are there from 0 to 15? There's 16. All over 1 minus 4/3. I will say I put this one in my calculator. This is not going to be nice. I mean, when you're raising 4/3 to the 16th power, it's not going to be nice. And so this is sum of 16 terms. Sum of the 16 terms, I got to be 592.65, just rounding. That's what I got to. Okay? Okay, finally, wrapping things up. Let's see how we're doing on time. About 12 minutes, good. What if we were to do an infinite geometric series? Like, what if we were to do this forever? I will say arithmetic, we don't really explore that because it would just go on forever. It'd go to infinity. If you add 2 to a number forever, it's going to go to infinity. If you add negative 2 to a number forever, it's going to go to negative infinity. But what if you're multiplying? You might think infinity also. Well, let's explore that. So what if you had the sum of an infinite number of terms? Follow your formula. It's, by the way, sometimes we put the A1 out front like this. You see that would be the same thing. So if I'm doing this an infinite number of times, it'd be r to the infinity. It's just kind of a little thought experiment here. What would that be? Well, r to the infinity, you're like, that's infinity. It can be. If r is greater than 1, or the absolute value is greater than 1, it will go to infinity. But what if r is less than 1? Now, if r is 1, it just stays 1. But what if r is less than 1? What is a number like 0.8 to the 800 equal to? Let's just put that in real quick. It is tiny. It is 2.96 times 10 to the negative 78. Basically 0. So if the number, what's happening is, we could say this: if the absolute value of r is less than 1, then, let me write the word then r to the infinity approaches 0. This is kind of a calculus idea, this arrow of approaching. It, for all intents and purposes, becomes 0. So, in this scenario, if that's true, we would say the infinite geometric series is a1 times 1 minus 0 over 1 minus r. Well, 1 minus 0 is just 1, right? And 1 times a1, so it just ends up being this, which is so simple looking. And these problems are actually very simple calculations, but it's just the first term divided by 1 minus the ratio. I'm going to show you one in an easy one first, and then a little bit harder one. Maybe you've heard of this example before. Imagine you are, let's say, 20 feet from a wall, and you're going to walk halfway to the wall in a minute. Every minute, you're going to go halfway to the wall. So in 1 minute, you're now 10 feet from the wall. Right? In the next minute, you're now 5 feet from the wall. In the next minute, you're 2.5 feet from the wall. The next minute, you're 1.25 feet from the wall. Then by the 5th minute, you're 0.625 from the wall. So when do you get there? Theoretically, you never get there. You become a fraction of some distance very, very quickly, but you never get to zero. Think about having a big, huge party sub sandwich, and you're going to cut it in half. And then one of the halves you cut in half, and then that half you cut in half, and that you cut in half, you continue to do that over and over. You never get to where there's no sandwich left, theoretically. Now, it'd be impossible after a certain number of cuts to actually do that. But, so in that wall example, let's say, to simplify it, let's say you're 1 unit away, okay? So in the first minute, you walk a mile away from some target. In the first hour, you go half a mile. The next hour, you go 1/4 of a mile. The next hour, you go 1/8 of a mile. The next hour, you go 1/16 of a mile. The next hour, you go 1/32 of a mile. And you do this forever. How far do you travel? Now, hopefully, you know that you're going to be getting really, really, really close to 1, right? Because you're going to be, so if you're approaching some fence post, you're going to have your nose to the fence post pretty quick. You never technically get there, but you're going to be a fraction, infinitesimal distance away. So this should equal 1. Let's see if it works. What is our R? R is 1/2. What is our A1? 1/2, right? I mean, that's our first term, and each term is multiplied by 1/2 as well. So that's all we need. That's all the formula calls for, right? Seems shocking, but the sum of these infinite terms would be 1/2 over 1 minus 1/2. It's going to work. You get 1, just like we were suspecting. Seems to work. And that's not proving it, but it seems pretty good. Well, let's do one more problem, and we will be done with this section. We'll make this a summation. A summation can have an infinity symbol up top. That means you're going to do this forever. Remember the number in the parentheses, the number being raised to the power is always your R. So I could write, let's go ahead and write it a few terms. So the first term would be 100 times 4/5 to the 1, plus 100 times 4/5. So that should be 0. To the 1, plus 100 times 4/5 squared. Okay, this is getting old forever. So that is just 1, so this becomes 100 plus 80 plus, what is that, 16 over 25, which makes this 64. It goes on and on and on. What's that going to add to? Gotta guess. You know, right now we're already at 224 or 244. So I don't know. Is it going to get to 500? I mean, the next one's going to be 80% of 64, which is going to be in the 40s. I don't know, maybe 3, 4, 5, 600, something like that. But it does it forever. Not just 100,000 times. Not just 10 million times. Billions, trillions. It doesn't stop. Well, let's see what happens. We only need 2 things. We need R1 is 100. We need R1, what am I saying? We need A1. A1 is 100, and we need R, which is 4/5. Let me clean that up a little bit there. One more time. There we go. A1 is 100. So this says you want to add up an infinite number of those terms. It's 100 divided by 1 minus 4/5, which is 100 over 1/5. And it's exactly 500. Exactly 500. Crazy, because, I mean, beyond this 64, we're going to have decimals. And the decimals are going to get insane. But they will get closer and closer and closer and closer and closer and closer to 500. So if you were to do, say, 10, 15, I don't know, 20 terms, you're going to see 499 point something, 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 probably by 15th term.